Hi everyone, welcome back. Lecture 2. So today we will talk about prefix-free codes and Kraft's inequality, which we will learn about shortly. Right, so let's start with the quiz from last time, which will also function as a recap of the last lecture. Okay, so we want to design fixed length codes for an alphabet of size 9. And the first question was, what is the length in bits per symbol for such a code? Right, and in last class we saw this formula that if your alphabet is like this X, then the bits per symbol is log base 2 the size of the alphabet, the ceiling of that. So in simple words, basically you find the nearest power of 2 which is bigger than your size, right? So 9 lies between 8 and 16. So you take 16, you take like log base 2 of 16, which is 4. And so 4 is the number of bits you need if you are going to represent this in a fixed length code. Is everybody okay with that? I think most of you got this one right, so that's good. Okay, so one thing you will immediately observe is like if your alphabet has size 8, then you're spending log 8 equal to 3, right? If it's 16, you are spending log 16, which is 4. So powers of 2, this seems to be working really nicely. But for 9, you see like clearly, like you want this, right? This is what you want. This is somewhere between 3 and 4. But this is not what you got. You got 4, which just seems like suboptimal. So this question was trying to introduce you to one idea to make it better, right? So the idea is simple. Rather than encoding one symbol at a time, you encode symbols in blocks of 2, right? So if your alphabet was like A, B, C, D up to like H, I, right? So the original code, what you would do is like A becomes 0000, B becomes 0001, so on, right, up to I. Now what you will do is you will create a new code, which is like AA, AB, AC, AD, ... right, up to II. So effectively what you are doing is you are creating an alphabet of size 81, right? You are creating the product alphabet of these two. And then we asked what is the length in bits per symbol for this code, like a fixed length code applied on blocks of 2. Here there were mistakes both on our side because we made a typo in the next question and which led to some of the students getting this wrong. But I think you got the concept right. So again we use the same trick. We know that 81 is less than equal to 128 and greater than 64, right? This is 2 power 7, this is 2 power 6. So really, if you calculate this will be 7. So many of you got it correct that you need 7 bits to represent this pair, right? So AA becomes like 7 bits. So this becomes 0000000, and then so on for the other guys. However, the question we asked was bits per symbol, not bits per block. So here the bits per symbol is each block has 2 symbols, right? So just to make it very clear, block is like AA and symbol is like A, right? So each symbol and then you have a block of 2. So the length in bits per symbol is this divided by 2, which is this divided by 2, which is 3.5. Yeah. And those who wrote 7, we will still give you marks because we made a mistake in the next part where so let me read the question. So now the alphabet size is 81 because we will be encoding pairs of symbols together. So the length in bits per, so this was the typo we made, it should be bits per block, is log 81 7. However, we are encoding blocks of 2 symbols, so the length in bits per symbol is this divided by 2, 3.5. And did working in blocks of 2 give a better compression ratio? And I think most of you got it right. The answer is yes, right? So we went from 4 bits per base, 4 bits per symbol when we were encoding them one at a time versus like 3.5. I wanted to do this. Can someone be kind and tell me what is log 9 base 2? I just want to see how close we got to that.
It's like
Okay. Yeah, it's 9 is very close to 8, right? So we assume it's only a little bit above log 8, which is 3. So we got to 3.5. We didn't quite get to log 9. Can somebody suggest how I can get even closer to this many bits per symbol?
Create larger blocks.
Yeah, very good. The answer was larger blocks, right? Simple idea. Instead of doing 2 at a time, you do 3 at a time. So you have like 9 cubed possibilities and so on. And you can keep going, and you can show actually, if you work, just do some math, that you will actually eventually converge to 3.17. And we will see this sort of scheme and even better ideas to achieve this, because you can see that this is not particularly optimal. Like, your alphabet is just growing exponentially as you make your block bigger and bigger. So we will come back to this. For now, I guess just notice that you can do better than fixed length codes by using some clever ideas. Okay. And any questions on this first question? Okay. Second one is very simple, right? This is the sort of quiz question, like you listen in class and you solve it like in a second, basically. So, yeah, I think everybody has got this right, but let me quickly do it. So the length, so the question is, you are given a random sequence which is sampled from some probability distribution, and you encode it with this code. You want to compute the expected code length, right, which is our usual like metric for determining the goodness of a code. So the length of each code word, you can just write 1, 2, 2, right, and then you can calculate the expectation. This is just making sure you remember your probability. So PA times length of A plus PB times length of B plus PC times length of C, which is 1 plus 0.3 times 2 . Okay, 1.5, I hope I got it right. Bits per symbol, right. I find it useful to always write the unit bits per symbol, because that way you don't make mistakes like the mistake that we made in the question. Yeah. Okay, any questions on this? Okay, good. Okay, I gave an exercise in the last class to decode this. Was anybody able to decode? So this was the code we gave, and I wrote down a sort of encoded sequence, and I wanted you to get back to the original sequence. I see a couple of hands. Anybody else? Okay, let me ask you for the first, and then I will ask you for the second. So what's the first symbol, first decoded symbol? So the answer given is D. And why is it D?
Because the only number that starts with a 1 and then has another 1 and has another 1 is D.
Right, and the answer is that, like, the reason why it can only be D, right? Because you have a code word which is like 111. Like if it was A, then it must have a 0 somewhere, and if it is B, then 10, so on, right? So there is only one possibility really, and we'll come back to this later in the lecture. The next one.
Yes, and the next letter would be like C, and then like we basically can just like keep reading each letter until we get to like a 0.
That's a good way of thinking, right? Like so the answer was, you just keep going until you hit a 0 because of the particular way this code is structured, right? When you hit a 0, if you have like 3 ones in a row without a 0, then you know it's a D, right? If you have 2 ones and then a 0, then you know it's a C, and so on. Let me decode a couple now. So after this you have 1. So when you see a 1, you know it's either B, C or D, right? It can't be A, so that's eliminated. And then you see a 0. So you immediately know it has to be a B, because if it was a C, then it will have a 1, 1, and D also will have a 1, 1. So it has to be a B. So, okay. And then you see a 0, and you know only one code word starts with a 0, which is an A, and so on, right? I hope you're decoding this at home, but I hope you get the gist that Even if you have a variable length code, right? This was a variable length code, and last lecture we had some concerns from students that how will you decode it? But you can see like there are variable length codes that can be decoded, and this is one example. And we'll look at it in more detail and like characterize when exactly can you decode these things. Any questions on this? Anybody who wasn't able to decode and doesn't fully understand the process right now? Okay. And we will go through like an actual algorithm for those who like to think in that way. Right. Okay, so the outline for today, no sense going through the list, like we'll get to them when we get to them. But the first item is we will define what do we mean by lossless compression in this context. And we'll discuss two specific categories of codes. Okay, so I will write down a few codes and I will ask you whether they are lossless or not. Okay, is this lossless? No. I hear no. Why is it not lossless? What? Yeah, because of the ambiguity in the sense that A and B have the same encoding. So clearly, if you see a zero, like you only see zeros, so you can never tell whether A or B was transmitted, right? So this is not lossless. This is very much not lossless. Okay, now this one. Is this lossless? So is it lossless or not?
It is. Oh, sorry. No.
It's not lossless. Anybody else who has a differing opinion? What do we mean by lossless, I guess, right? Like if you know you're only going to ever send like one symbol, then this is lossless, right? If you see 1 0, then it's an A. If you see 2 zeros, then it's a B, right? So in that sense, it is lossless. But very rarely do you want to send only one symbol. Most often you want to send a sequence of symbols. And in that context, if you see like A will encode to 0 0, B will also encode to 0 0. So if you receive a 0 0, you don't know whether the original person sent a AA or a B, right? So in that sense, it's not lossless. But you already start saying that like the definition of lossless is not obvious, right? Like you need to define it carefully. Otherwise, it's not clear what do you mean when you say it's a lossless code. Yeah, so let's define it. Yeah. Okay. So we will define something called a uniquely decodable code, and it's a very simple definition. So a code is uniquely decodable if no two input sequences, say xn, ym, where m and n are greater than or equal to 1, are encoded to the same code, or I guess let's call it same output. Are we happy with that definition? Any questions on this definition? Right. So with this definition, if we go back, or let me draw that again. So like this code that we saw, A was 0, B was 0, 0 is not uniquely decodable. Before we move on, so when we talk, for example, right, we have a sequence of words, right, and sometimes you have two words such that like they are individually words, but when you join them, that's another word. That's possible in English, for example. So when you talk, right, and you talk to someone, how does the other person know when does the word end and when does the other word start? Forget about codes for a second, just like very generally. You have spaces. Very good, right. So oftentimes, like this is one way of thinking about it, right? Because the way we are thinking about it is when you have AA is encoded to 0, 0 without any gap, right? It's just 0 followed by 0. There isn't a gap. B is also 0, 0, no gaps anywhere. So that's the sort of setting where we are thinking about these uniquely decodable codes. And most often when you're working in any real application today with computers and so on, you can't afford gaps because you have a binary alphabet you're working with. You have 0 or you have 1, right? You don't have a third symbol to signify that, okay, like now one code word has ended. Now we will pause for a sec. In the old days, some of you might have heard of the Morse code. So this was used in the telegraph, which was the only mode of like intercontinental communication for a long period. And even like during my dad's time, like that was the way people sent fast messages in India. So Morse code is comprised of dots and dashes. So it's a way to like, you can represent any letter or any number in this code. And you have a dot or you have a dash. So let's look at the code and then we'll come back. You can see this, right? Yeah. So for example, E is a dot, right? S is a dot, dot, dot. Q is a dash, dash, dot, dash, right? So you just send a sequence of these. And on the other side, just listening to the dot, dash, the other person can decode it. So this was the Morse code. And how did the Morse code denote the separation? So I guess if you look at this, you will immediately see that you have E, you have A, and you have T, right? If you look at these three, so a E followed by a T is a dot followed by a dash, but an A is also a dot followed by a dash, right? So Morse code in our sense is not uniquely decodable, right? So this is not uniquely decodable in the way we think about it, but clearly it was used for communication for a long period. And why is that? Because between letters you would just put a space, like you will pause, like you will not send anything for a bit, and then you will start sending the next letter, right? And then the receiver would know how to like, I guess initially some human used to do it and then they made machines. But the idea is that in different types of communication systems, you can have different ways of doing things, right? Like for us, like this is very important. This is what we'll be working with, and this is how most modern compression algorithms work. But there are other systems also. So you should be aware. Like putting a comma after every letter in a way. Okay. Anything interesting somebody observes, like anything that we saw in the last class and you see reflected here? Like look at the lengths of the different code words. Anybody wants to like, what do you see here? Anything interesting with the letters and which letters are getting shorter codes and which letters are getting longer codes? Good. Yeah, so the vowels are shorter. That's one suggestion, and that's true. E is a single dot, I is a dot dot. Some of the vowels are a bit longer, like U is a dot dot dash, right? But you see T is very short, right? And if you study like the frequency of letters in English, you will see that E and T are the two most commonly used letters, right? So the vowels are shorter, because they are also usually very commonly used. So even in the Morse code in those old days, they knew that for more frequently used letters, you should use a shorter symbol so that your overall message becomes shorter, right? So that's just, I think, an interesting fact. Any questions with this?
Could you go back to the previous slide?
This one? Yeah.
And the previous one.
Yeah.
Yeah, so the X and then Y and
So they are just two input sequences, right? So if we were to give an example, right here, if you take X2, so which is like two tuple sort of X1 comma X2, which is like A comma A, or you take Y1, which is just a single input, which is B, then you can see that the encoding of X2 is the same as the encoding of Y1, which is 0, 0. So that's what we meant. Sorry if the notation is new. I think I will define it more properly in the next part, or you will also get used to it. But yeah, that's just a tuple X2 or Xn. So we are saying that it's not like N and M don't need to be the same, right? Any two sequences with different lengths, they should never map to the same output. Right? It should be unique. Like given the output, you are not only able to decode, you also know how many input symbols were there. So it's a very strict property in that. Is that clear? Okay. Yeah. So we will not talk about uniquely decodable codes for the rest of the class. You will see a question in the homework, and I will explain later why we don't talk about these. It's a very powerful property, but you don't really need this very powerful property. We will see a much smaller class of codes, which is very, very easy to deal with, and we'll just stick to those. So that's our next topic. Yeah, but there will be a homework question where you will look at these and do some proofs with these. Okay. Let me find the old code we had. Yeah. So this is a proposed decoding algorithm for this code. Let me talk through this in words. So you start with an empty, you have a variable called C, which is like storing your sort of code, like the encoding. You start with empty. You look at the next bit, you add it to C. You check if C is in the table, right? So if C is in one of these 4 entries. If C is there, you decode. And then you set C again to like empty. And if C is not in the table, you just continue and then look for the next bit and you keep adding the bit. Right? So a very simple algorithm, linear time and so on. I will do an example, but before that, do people like generally understand the idea behind the thing? Okay, let me do an example. I think that should help. Yeah. And as Pulkit said, like, apologies if you have done information theory and all this, I think, probably this lecture and the next lecture will be mostly recap for the info theory experts, but after that you will see a lot of new material. Okay, so let's do an example for the same code. So we have, let's say, 0, 1, 1, 0, 0, 0, something. Okay. So we do it step by step, right? First step, C is equal to 0. Sorry, first step, C is nothing. So null, okay. Then C is 0. You decode A, right? Because you immediately see that 0 is in this table here. So you decode. So this is your code word you're trying to decode. Then C again becomes empty. Then you put C equal to 1. You can't decode here. There is no code word which is 1. Then you see C is 1, 1. Again, there is no code word which is 1, 1. Then you see C is 1, 1, 0. And here you can decode C. Okay, can somebody help me with the next few steps? What happens next in this? So after I decode C, what is the value of my variable C? Yeah, C becomes empty again. Right after you decode, you reset C. Okay, next step. So we are here basically. Next symbol is this one. Yeah, so next step you insert 0 in C, right? Are we ready to decode? Yeah, why are we ready to decode? Because 0 is one of the code words, right? 0 is the encoding of A, so you immediately decode A. And so on. Let's not do it too much. Okay. So let's think about this. First of all, any confusion with this? Are we happy with the decoding? Right. Why do we think this works? What is the property of the code that makes this possible?
Basically, like, no code is like the prefix like at the beginning of any other code.
Yeah, so the answer given by student, which is the correct answer, is that no code word is a prefix of another code word. So you see, 0 is not a prefix of any of these. So as soon as you see a 0, you immediately know that it has to be A, because there is no other code word that starts with a 0. Right? B, 10. 10 is not a prefix of any of the other guys. So as soon as you see a 10, you know it has to be a B. It can't be C, it can't be D, it can't be A. And so on for the other ones. So let me define it. So there are a few different names for some historical reasons, I assume. So they are called prefix codes. They are called prefix-free codes. They are also called instantaneous codes. Okay, figure it out. Instantaneous codes, right. So no code word is a prefix of another code word. Right, stop me if you don't follow. Why are they called instantaneous? We just saw that property, right? As we were trying to decode, as soon as we saw the symbol, we were able to decode it like instantly, right? We saw 0, we decoded A. We saw 110, we decoded C. You don't need to look ahead, right? You can do it in a more streaming way. As your symbols as your bits are coming in, you are immediately able to decode. That's why it's called instantaneous code. Why is it called prefix-free code? Just the definition and yeah. Why is it called prefix codes? I think just people didn't want to write prefix-free all the time. Okay. So just a simple property. Prefix-free codes are uniquely decodable, right? So the property we saw earlier, right? The uniquely decodable property that no two sequences map to the same code. Prefix-free codes satisfy that condition. Can somebody intuitively describe why? We won't do a formal proof of this, but just intuitively, can somebody suggest like why are prefix-free codes uniquely decodable? Why are they lossless?
When you go through the algorithm and you find C in the table, you are 100% guaranteed that it's not just a part of another code word. It's that it is going to be exactly C or exactly whatever you find.
Yeah, very good. Yeah, so the answer was as you are doing the decoding, right, and you decode 110 to C, you know it has to be C. There is no other option really, right? So in a way, the decoding algorithm proves that it's decodable uniquely, right? There is that decoding algorithm, and if you have done math, you will want to be more formal, and we will leave you to read the textbook if you want like very formal proofs. But it's intuitively correct, and you just like write that in math and you get the actual proof. But they are uniquely decodable because there is a decoding algorithm which there is no confusion. Like you start from the beginning and you can just decode the sequence. There are no options really. Do we think the opposite is also true? Let me not dwell on that too much, but it is not. So uniquely decodable does not imply it is prefix free. So there are uniquely decodable codes which are not prefix free. And you will see examples in homework. But again, we will see that prefix-free codes are good enough for anything we want to do, really. So we will not study uniquely decodable. Like we will not study codes that are uniquely decodable but not prefix-free. That's a category we will just not worry about too much. Okay. Any questions about this? We will talk about the prefix codes throughout the lecture. Hopefully by the end of it you will feel very comfortable with them. Okay, so second topic in the outline. So we saw one algorithm to decode prefix-free codes already somewhere here, right? You start with something and then you keep adding bits until you find something, right? This is one algorithm. We will see another algorithm. How many of you have done like a algorithms class or data structures, seen trees? Okay, nice. A few of you have seen trees. Okay. Even if you have not, you will see trees now, so you will learn something. Okay. So let's again make our favorite code. Okay. So what we will do is we will map code words to leaves of a binary tree. So you start with a root, right? Every binary tree has a root, right? And a binary tree will any node in the tree will be either a leaf or it will have two children. So the root here has two children. One is the left child, which we'll call 0, and the right child is 1. And A is the leaf here. Okay. Let me draw it and then we'll discuss. Very simple stuff really, if you think about it. right? So the path from the root to the leaf gives you the code word basically, right? So if we write it down, so path from root to leaf equal to code word. Any questions? This is just a representation, and we'll briefly talk about like why this is interesting, and then we will use it in a bunch of proofs. Right. Okay. So let me just describe you another method of decoding that will use this tree. Okay. So the algorithm is simple, and I think you will implement, maybe, yeah. You will see the code for this next lecture as well. Okay. So you first see a 0. So what you do is you start at the root, you follow the 0 branch, right? If you reach a leaf, you immediately decode, okay, A. And then you go back to the root. So you reset, right? That's the reset step in a way. Now you're at the root again. You see a 1, you go here. You see another 1, you go again. You see a 0, you come here. You see, oh, I've hit a leaf, right? So I have a leaf, so I decode C, right? And then I again go back to the root from here. Then I see a 1, I go here. I see a 0, I go here. I hit a leaf, I am at B, I decode B. Right? Are we happy? Should I explain again? Okay. Okay. We'll keep moving, and I hope you get some practice in homeworks. You will see this several times. Okay. Okay. So now a question for everybody. Please help me. I have this other code. Please help me make a tree out of this code. And I will make the root for you, and I will put the A here. Right. But can you help me with the B and the C? Anybody? Okay. So the suggestion is to make the 1 branch definitely, because B and C both start with the 1. Makes sense. Okay. Yep, we make a 0 branch. Yep.
Then we write B.
I write a B. Yep.
Create 0 branch from
Does this look different from the other one in some way? Forget about the fact that some of the nodes don't have 2 children. That's fine, I think. Are there any other ways in which this differs from the previous one? Yes.
Yeah, essentially here's like C, it's a child of B. Like it's and it's meant, like in the other one, once you got to a letter, there's no children that come after it.
Yeah. So the answer is basically that here C is a child of B, right? So B is not really a leaf, right? So B is not a leaf, and the reason is that B is a prefix of C, right? So B is prefix of C. You see 10 is a prefix of 100. So since B is a prefix of C, it's not a leaf. This is not a prefix free code. It's not a prefix so basically. So this is a property which again will not prove but very intuitive, is that